Let's look at this problem. It takes Bob 3 days to paint a house. It takes Ralph 2 days to paint a house. How long would it take them to paint a house together? That is, they're both painting at the same time. How long would it take? Before we answer the specific question though, let's try to better understand the problem. So in a previous video, I talked about the things that I would do to try to understand word problems. Now this particular type of word problem is called a rate problem. And the reason why is because we're given these rates at which they can operate. So let B equal Bob's rate. And in this case, we happen to have what it is. We're not going to solve for it. It's equal to, we can write it two different ways. It says it takes 3 days to paint a house. So we can think of it as one house per 3 days, or 1/3 of a house per day. Mathematically, these are equivalent, but the first one is really the easier one to work with. And then we have Ralph's rate, and once again, we're not going to solve it, we're already given it. Is one house per 2 days. I also said in another video that we need to have domain knowledge. So what's the domain knowledge we need to know here? Well, we need to know something about the relationship between how long, this is a measure of time, and the rates that we're given. And so what can we use here? Notice I've also been writing units. So here we have houses per day, and ultimately we're going to have the number of houses. So what do we need to get from here to here? How long? This is time, right? In days. So we have a rate, 3 days to paint a house, so number of houses per day. How long, this is in days, would it take them to paint a house? That's the number of houses painted. Because remember, we could cancel out the days, leaving house over here and house over here. So this would be for one person. So let's think about what we're dealing with. Let's talk about if just Bob is painting. So we'll think of this as being the house. So what happens after 1 day? We have 1/3 of the house, right? So we would have one house per 3 days. And multiply that by 1 day. This is 1/3 of a house. This part right here. And if he paints a second day, we get this right here. Paints a third day, we get this right here. Okay? So really we have three things here. We have the rate, we have the time, and we have the amount. And in other types of problems, amount would be different things. This is measured in houses completed, okay, or painted. So here's the basic idea. We also could think of this as being a functional relationship. So we're used to seeing functions in something like this. If we're going to think about drawing a line, y equals mx plus b. Okay? So what are the parts we have here? Well, y is the house, or how much house is painted. M is our rate. House per day. Number of days. And then the B is 0 here. So we're looking at this. So days, 1 day, 1/3 of a house. So this is amount of houses painted. 2 days, 2/3 of the house, and so on. Okay? So that's the basic idea. So how do we answer the actual problem? Let's think about what we have here now. So now our house looks like this. And we can think of Bob as working on this end, Ralph working on this end, and they work towards each other. Now Ralph happens to be painting faster, right? Because he can paint a house in 2 days. Well, it takes 3 days for Bob. So they should meet somewhere over here. So what do we have? We have Bob's part plus Ralph's part
I've got mail
equals what? One house. So how do we represent each of these? Well, it goes back to what I had before. Bob's part is something like this. So for Bob's part, we have this. One house for every 3 days times the amount of time he spent. So we'll say this is T1 plus one house per 2 days for Ralph times the amount of time he spent was T2 equals total houses. Now, as it's written now, we have a problem. I have a single equation, but 2 unknowns. So technically, there's an infinite number of combinations of T1s and T2s that can satisfy this. So what can we do about that? When we talk about them working together, we're assuming they start at the same time, and then they stop when they run into each other, which means they stop at the same time. So what we really have is that T1 is equal to T2, and therefore we'll just represent both of them as just T. So it says how long, we're trying to find the T that satisfies this. So what do we do with this? So 1/3 T plus 1/2 T equals 1. I'm dropping the units to make it easier to write because I've used those to sort of check that I had the right equation and to better understand the problem. So what does this become? 1/3 plus 1/2 times T, use the distributive property, equals 1. So this becomes what? 2/6 plus 3/6 T equals 1, right? 2 over 2 times this, 3 over 3 times this gives us this, which is 5/6 T equals 1. And we get that T is equal to 6/5 of a day. So slightly over 1, it's 1 1/5 days. Does that seem to make sense? Well, we know Ralph could do it in 2 days by himself. So with Bob helping him, it has to be less than 2, and this is less than 2. And then Ralph, would be 3 days by himself, so obviously it has to be less than 3, but the 2 is the smaller of the 2. Okay? Does this work out? 1/3 times 6/5 plus 1/2 times 6/5 equals 1. So here we have 2/5 of the house plus 3/5 of the house, right, equals 1. So it does work out. Okay, so there's an example of a rate problem. I'll make another video that picks up on where this problem left off.